Greetings, everyone. Today we're going to explore Cramer's Rule. In your notes, don't forget to add a left column. All right, so where does the name Cramer's Rule come from? Gabriel Cramer was a Swiss mathematician in the 1700s, and what he discovered is that he could use matrices to solve systems of equations. So why is it useful? Well, we're going to work through an elimination example using all variables. So you can see how the determinant we will be using is helpful in solving. So as we take a look at this next slide, you don't need to write anything down. I know it seems very cumbersome with all variables, but it sort of sets that foundation in order for us to actually use systems with numbers to solve. So let's say you start off with a system such as this. You have a coefficient of A, a coefficient of B, a solution of C. You have another coefficient of D, a coefficient of E, and a solution of F. It looks like your standard form equation that we've used elimination for in the past. So let's just pick Y, and we're going to eliminate Y. In order to eliminate Y, that means I need to multiply each equation by the opposite coefficient, and I need to make one of them a negative. So I'm going to take the entire first equation and multiply it by the opposite coefficient, which is E, and take the bottom equation and multiply that by the opposite coefficient, which is B. But I need to have a negative on it, right? Because in order for it to cancel or eliminate, one needs to be positive, one negative. So if I distribute that variable, you can see it here on the right. Now, if we actually use elimination and long addition, if we add the columns, let's see what happens. We actually, the entire Y terms eliminate, and we end up with AEX, the top value, still subtracting BDX, the bottom value, and then on the solution side, we have CE minus BF. It's a lot of letters, but let's keep going with it and see what happens. Let's say I want to try simplifying and I want to solve for X. If I'm solving for X, this has been on all of our learning checks recently, I need to factor out an X. Once I factor that X out, I can get it by itself by dividing both sides by that entire set of parentheses. So now, if I take a look at that, let's make some comparisons here. I can see CE minus BF and AE minus BD, which is a form of a determinant. Okay, so that was our last video, was finding a determinant. So if you need to review that, please take a look. So what that means is I technically have the determinant divided by a determinant. Okay, if I take a look here and I compare letters, I've got C, B, F, E, and I have A, B, D, E. Okay, so I've got a determinant over top, determinant, which is going to possibly leave me with a fraction or possibly a whole number. So let's actually apply this. Let's take all those letters and try to make more sense of them. Let's look at it mathematically with values that we can solve and use. So first of all, talking about coefficient matrices. You can make a matrix out of the coefficients from a linear system. So coefficients, keyword, right? The number in front of our variables. You can also make a matrix out of the answers as well. So for example, I have this linear system, right? So we're going to stick with a couple letters here. And if I made it into a matrix, this would be my coefficient matrix, meaning every coefficient put into a matrix. And then I can also have an answer matrix. And all that means is I'm taking the answers and turning them into a matrix, specifically a 2x1 matrix. Okay, so this is just vocab that I'm going to use that you need to understand. So how do I actually apply Cramer's rule? Let's go through the steps first. The first thing you're going to do is build the coefficient matrix and the answer matrix. So literally you're going to take the system of equations, put it in matrix form. That's it for step one. For the second step, you're going to find the determinant of the coefficient matrix. We'll start off simple with just 2x2 systems, so it shouldn't be too bad for the determinant. If you need a refresher on this one, that would be the previous video, so you can take a look at my YouTube channel. The third step, to find x, we're going to replace the first column of the coefficient matrix with the answer matrix. Okay, so we're going to flip two columns. We're going to replace the first column with the answer matrix, and then we're going to find another determinant. So we've found two determinants so far. Well, what we do to x, we're also going to do to y. So now I need to replace the second column with the answer matrix and find the determinant. So we're on to our third determinant. Step 5, we'll be able to actually find the answer of our systems. And we're going to do that by taking the determinant of our x matrix, and we're going to put it over our determinant of our coefficient matrix. Okay, so if I relate these steps, here's how I could relate that. I could say that this is the determinant A, that's step 2. So the denominator is from step 2. Okay, and then this numerator, this would be from step 3, and y is from our step 4. Okay. Now, it seems kind of busy, but in the end, it's going to be a number over a number. It's going to be a very basic calculation. What actually takes some work here is really going to be steps 3 and 4. Okay, so let's apply this idea of solving systems using coefficient matrices and determinants. So for our first thing, I see a basic system. Yes, I know you could use this with elimination. We'll get to more of the why later. So my first step is to create a coefficient and an answer matrix. Okay, so my coefficient matrix is going to be just like it's laid out, the coefficient of 8, 5, 2, -4. And then I need an answer matrix of 2 and -10. Easy first step, okay? Second step, I need to find the determinant of my coefficient matrix, okay? So that means I need to take 8 times -4, and I need to subtract 2 times 5. The nice thing about a 2x2 matrix is the determinants are easy to find. So that leaves me with a -32 minus 10, which is equal to -42. So that's an important number there. That's the determinant of our coefficient matrix. Okay. So mathematically not bad, it's just the steps we're following. Step 3. Okay, we want to find x. So we're going to start off. We're going to replace our x's, meaning our first column, with our answer matrix. Okay. So that means, sorry, really bad writing there. Oh my goodness. Answer So that means instead of 8 and 2, I'm going to have 2 and negative 10. Okay, took that from my answer matrix. And then I'm going to keep the 5 and 4 from the coefficient matrix. Okay, oops, that's a negative 4. Now we want to find the determinant. Okay, it's a 2 by 2, so when I look at this column, I've got 2 times negative 4, subtract this diagonal, sorry, I said column earlier, I meant diagonal. I have a negative 10 times a 5, multiply that out, negative 8 plus 50, that gets us to 42. Okay, so that's our determinant for x, if I was to generalize that. Okay, step 4, now I need to deal with my y's, which means the x's are going to stay the same. Okay, so I'm actually going to try to color coordinate here a little bit. So we keep the x's from our original matrix, but now what's new is I'm going to put the answer matrix in for y. I now want to find the determinant, so I'm going to have 8 times negative 10, subtract 2 times 2, so that gets me to, what do we got, negative 80 minus 4, so that gets us to negative 84. Important number. Okay, now step 5, our last step, okay, is to create those fractions, and that's going to help us find our x and our y values. So I like to set it up first. I'm going to have 2 fractions always, okay? Our determinant of our coefficient matrix is always our denominator. It's always our base. Think about that. It's a foundation for the rest of the problem. And so that foundation's got to be underneath to hold everything up. All right. Now for x, I want to take the value from when we were replacing x with the answers. Okay, so when we dealt with the x column. And then for y's, when I dealt with the y column, I want to use the determinant that we found there. If I take a look how nice this worked out. Our x value is a negative 1 if I simplify, and my y value is a 2. Okay, so look how that worked out. Pretty straightforward answer. Well, we know that's the case because we could have done this using elimination, right? And you're like, Mrs. Morfett, why are we doing all this extra work? You'll find out, I promise. Right now, I just want you to concentrate on this process. All right, so let's take a look at another example. We really need to get this process down, okay? So first step is to create your coefficient matrix. Be careful with your signs and our answer matrix. All right, next step is to find the determinant of our coefficient matrix. Okay, so that means I take that original, it's going to be the foundation or the base of everything, multiply diagonal, so that gets me to negative 4, subtract multiplying the diagonal, which is 3. That gets me to a negative 7. Important value there, okay? Next step, step 3, I want to deal with the x's, okay? So that means I need to change my x column. All right, that means I'm going to keep the y column, but I'm going to change the x column to my answer matrix or my answer column. Let's find the determinant. 1 times negative 2 is negative 2. Subtract the other diagonal, which is 1 times negative 23. Changes to adding, and we end up with 21. Okay, that's very important for our x solving. All right, step 4, let's deal with the y's. So what that means is we're going to keep the original x values, but now I'm going to replace the y values with the answer column. Let's find the determinant. Multiply the diagonals, which gets me to negative 46. Subtract, multiply diagonals, which gets me to 3. If I subtract those, I'm at negative 49. Very important number. Okay, and our last step is I want to solve for x and y. They both are created from a fraction. Okay? That fraction is held up by the base, the foundation, which is the original determinant of my coefficient matrix. So that -7 is very important. It holds up my other values. My determinant for x, my determinant for when I was working with the y values. And if I simplify those fractions, I get my solution. Nice and clean, a -3 and a +7 is my solution. All right, the nice thing about this, if you wanted to solve using elimination, that would prove that you're right. But in this case, I'm going to look for these steps, okay? All right, keep hanging in there. Let's take a look at solving a 3 by 3. This is going to get a little crazy, okay? Because we have to replace 3 columns, an x column, a y column, and a z column, all right? So let's go through the basics though. All right, first step, create your coefficient matrix and your answer matrix. Coefficient matrix is 1, 3, -1, -2, -6, 1, 3, 5, -2. Our answer matrix is going to be 1, -3, 4. Easy first step. Okay, part 2. We want to find the determinant of our coefficient matrix. Now this is a 3 by 3. You might need to watch the previous video if you need a refresher on finding the determinant of a 3 by 3. Remember, your first step was to copy these 2 columns over. Okay, that way we cover all of our bases, all of our numbers. Next, I want to look at my diagonals, multiply, and come up with that total as I go down the diagonal. So 1 times -6 times -2, +12. Let's do the next diagonal. 3 times 1 times 3 is 9. -1 times -2 times 5 is 10. All right, what do we do with those multiplied values? We add them together. So in this case, let's see, 2231 is what I got there. Now, let's take care of the up diagonals going up. 3 times -6 times -1. Okay, looks like that's going to get me to 18. 5 times 1 times 1 is 5. -2 times -2 times 3 is going to get me to 12. If I add those together, we're going to end up with 35. So remember, to find that determinant, we've got 2 numbers. We only want 1 value for the determinant of the coefficient matrix. So we always take the first piece of work and subtract the second piece of work. So in this case, we end up with a -4 for my determinant of the coefficient matrix. All right, I need a little more room, so let's carry over that information. The determinant of our coefficient matrix, which is the foundation for everything we're going to do from here on out, and that value is -4. So I'm just going to keep that off to the side there for myself. Next, we're going to take a look. I need to deal with my x values. So for step 2, that means my x column is going to be replaced with my answer matrix. So 1, -3, 4. But that means we keep all of the y and z values. So carry those over. Now, because this is a 3 by 3 and I'm trying to find its determinant, I need to copy over my first 2 columns in order to cover all my bases. Okay, so now if I go down, 1 times -6 times -2 is 12. 3 times 1 times 4 is 12. And -1 times -3 times 5, looks like that gets me to 15. Okay, So if I add those together, what do we get? 12, 24, 34, 39. Okay. All right, let's take care of our other diagonals. 4 times 6 times -1. Looks like that gets me to 24. 5 times 1 times 1, 5. And -2 times -3 times 3 gets me to 18. If I add those together, we should end up with, check with me, 47 is what I got. All right, so that's not the end though. To find that determinant, I need to take that 39, my original work, subtract my secondary work, and we end up with -8. Okay, so determinant, I'm going to say x. That just makes sense to me because that's the value I'm working with. And I'm going to say that's currently -8. All right, next step, we're going to take a look at dealing with the y values. So that means I'm going to replace my y column with my answer matrix. So now that's going to become my 1, my -3, and my 4, which means I keep the original x and z values. All right, so I'm going to my pen here to work. My x values were originally 1, -2, 3. My z values, -1, 1, -2. So I want to find the determinant of this matrix. So let's take a look at my columns. All right, I've got 1 times -3 times -2, 6. Look, if I go to find that diagonal, I'm missing values, so that's a good reminder that I need to copy my first 2 columns over. So you'll hit this roadblock if you forget that step. All right, let's try that again. 1 times 1 times 3. There we go, that worked out as I needed. -1 times -2 times 4 gets me to 8. So for my original setup of work, I've got 17. Look at our other diagonals. 3 times -3 times -1 gets me to 9. 4 times 1 times 1, 4. -2 times -2 times 1, 4. Let's add those together. Looks like we end up with 17. So when I take my original minus my second work, I end up with 0. Okay, so if I take a look, I'm going to generalize it. Determinant dealing with y ends up being 0. That's okay. Let's go with it. Fourth step. Okay, I need to deal with my z values. So that means my z's are going to be replaced by my answer matrix. And that means my original x and y values will stay the same. All right, let's find our determinants, but in order to do that, I need to copy over my first 2 columns. Okay, let's find that determinant. 1 times -6 times 4, -24. 3 times 3 times 3, we've got a negative in there, so we got 927. And then 1 times -2 times 5, I've got a -10. Okay, so let's take a look. I've got a -24. Oops, I don't know why I put subtractions because they were negative. Sorry, I was going to say I need to add. We're subtracting 27 and we're subtracting 10. So we're all the way up to, I've got -61 there. Okay. All right, let's take a look at the other columns. 3 times -6 times 1, -18. Sorry, I said columns, I meant to say diagonals. 5 times -1, 5 times -3 times 1, I'm jumping ahead of myself, -15. 4 times -2 times 3, so we got -8, -24. Oh boy, so I've got -18, I'm subtracting 15, and I'm subtracting 24. So I ended up with a -57. How does that sound? All right, so if I take those values, negative 61 subtract negative 57, so that changes to adding. So we end up with negative 4. Negative 4. Sorry, it's kind of crunched there. So pretty comparable numbers in the end. We've got a negative 4, a negative 8, a 0, and a negative 4. So those are the numbers that matter right now. Okay, so I'm going to kind of try to circle what we're dealing with. Negative 4, negative 8, 0, negative 4. So my fifth step is if I'm going to deal with finding my x, my y, and my z value, the foundation, the base of all of these fractions is going to be that negative 4, the determinant of the coefficient matrix. The x value that we were working with was negative 8, the y value was 0, and the z value was negative 4. If I simplify those, I end up with 2, 0, and 1. Simple numbers, they look like the typical solution we're used to, okay? So, as I look at that, that is the solution to my 3x3 system. I'll bring this example up and I'm not gonna go through this one, okay? I'm gonna leave this one for you to practice with and to try, see what kind of questions arise and see what happens. If you have questions, let me know in class. Okay, so whoa, that was like the steps are easy, right? It's just remembering all of those steps. The actual numerical calculations are simple. And so why all those steps? That 3x3 system took way longer than if we used elimination methods that we're used to. And so the reason why, you'll likely find out in next class, but just to lead you there a little bit, is we're going to start using the calculator. Okay, so the calculator takes care of finding those determinants for us. So how handy is that? If it could find the determinants, I can set up fraction, fraction, fraction. There's the solution to my 3x3 system. And all I had to do was type in the numbers. Okay, so it's going to be much more efficient in the future. I know it's not right now, but just wait. It will be, I promise. Until next time, have a good one.